Hello students, in this video lecture, I am going to cover up various strategies to handle the deadlock. There are four techniques to handle the deadlock. We will go through the one by one. So these are the four strategies are deadlock prevention, deadlock avoidance, deadlock detection and recovery, and ignorance of deadlock. So this is the last strategy in which we will never take care of the deadlock. We will allow if it will happen, then it's okay. If it will not happen, then it's okay. We will go through it, whatever the condition we have initially. But these are the three important techniques. So we will discuss one by one. First one is the deadlock prevention. For occurrence of deadlock, each of four necessary conditions must be held simultaneously. By ensuring at least one of these conditions cannot hold, we can prevent the deadlock. So how we can prevent the deadlock, we will discuss in the next few slides. First one is the mutual exclusion. The mutual exclusion condition must hold, that is, at least one of the resource must be non-shareable. According to the mutual exclusion condition, there there will be a non-shareable resource in the system. There should be non-shareable resource. So here we are considering a shareable resource in the system. If the system has the shareable resource, in that case, that we can prevent by sharing the resource. We can avoid the mutual exclusion condition, and that's why we can prevent the deadlock. If several processes attempt to open a read-only file at the same time, they can be granted simultaneously access to the file. A process never need to wait for the shareable resource. So by making a resource in the shareable mode, we can violate the mutual exclusion condition, and that's why, and by this we can prevent the deadlock. Second one is the hold and wait. To ensure the hold and wait condition never occur in the system, we must guarantee that whether a process requests a resource is does not hold any of the other resources. Means if I am requesting for the resource, some of the resources from the system, then initially I should not have any of the resource. So for this, we have the two approaches. In first approach, a process is allowed it to acquire the resource it desired at the current moment. After acquiring the resource is start execution. Now, before making any request, it is compulsory to release all the resources that holds currently. So, in the first resource, whatever the resource I have initially, I will go through that. If I requires more number of resource, so I must release all of the resource that I have, and then after request to the system, the entire resource. Suppose that I have hold four resource, I require two more resource, so I will release the firstly all four resources that I have. Then after I will request to the system the six resource that I want. In the second approach, a timer is set after the process acquire the resource. After the timer expired, the process has compulsorily released the resources. Means I am allocating the resource to you for this much amount of time, and after that you have to free those resources and return back to the system. For example, college has allocated a position to me, and now I required a new position. So firstly, I must release that position. Then after I will go for the new position. Or in the simple way, we can say after certain time of interval, I will release some of the resources that I have hold. So if you want to enter, suppose that you are in the third semester and you want to go into the fourth semester, so you have to return back the books after completion of the third semester to the system, means to the college. And then after you will request for the new books from the system. So this is the procedure. So here the time duration is the 6 month for which you have the books are allocated the books to you. No permission. The third necessary condition for the deadlock is the no permission. No one can print the resource from any of the process. To ensure this condition does not hold, we can use the following protocol. If process is holding some resource and requesting the another resource that cannot be immediately allocated to it, that is, the process must wait. Then all the resources that the process currently holding are preempted. Means I have the four resource and I want two more resources. So voluntarily I have to release my four resources. When I am releasing my resources, that means I am violating the condition of the preemption, because my execution is not completed till yet. I am still in the middle, but I have to release the resources. So automatically, no permission condition will get violated. Circular wait. This condition can be violated by not allowing the process to wait the resource in the cyclic manner. To violate this condition, the following approach is followed. A natural number is assigned to every resources. Each process is allowed to request for the resource either in only increasing, order. Means I if I require two resources, then after I have required the three resources, not the increasing and decreasing order. In case increasing order is followed, if a process requires a lesser number of resources, then it must release all the resources having larger number. So if I require the resource that have the number 10, and I have a resource I have a resource that has the number 10, and I requires a resource that has the number 8. So firstly I have to release the resource number 10. This approach is most practical approach and implementable. Now, coming on the deadlock avoidance. This approach to the deadlock problem anticipate the deadlock before actually occur. In this strategy, maintain a set of data using which a decision is made whether to entertain a new request or not. Means I am a process and I am requesting for four resources to the system. So firstly, system will check whether should my should the resource is granted to me or not. So it will be checked. It may be possible if resources are allocated to me and in the middle I need more resources and I am holding those four resources. So this may be possible. Some other tasks may not get completed due to the resource that I am holding. So I must release the resources. So if entertaining the new request causes the system to move in unsafe state, then it will be discarded. If the system will not be in the safe state, then my request will not be granted. This strategy requires that every process declares the maximum requirement of each resource type in the beginning. What is I need, which resource I need, and how much instance of that resource I requires during the execution. So Banker's algorithm is an example of the deadlock avoidance strategy. So using the Banker's algorithm, we can avoid the deadlock. For this, we have to find out the safe sequence. Safe sequence basically is the execution of the process in a particular sequence. Firstly, P1 process will get executed, then P2, then P3, then P4, or P1, P4, P3, P2, and so on. So, safe sequence basically the pattern, the order in which the process will get executed. Now, there is a very much important conclusion. It's there. If a system is in the safe state, then there will be no deadlock. If the system is in the unsafe state and there exists a safe sequence, then there will be no deadlock. If safe sequence is not existing, then there will be definitely deadlock. Now, coming on the Banker's algorithm basically term is taken from banking system. Whether should I grant a loan to you or not, this should not be there if I am allocating the loan to you, and by which the other customer may get affected. So I will check the order in which I will grant the loan. So here the data structure used by the banker's algorithm. Let n is the number of process and m is the maximum number of resource. So here is data structure available. It is a vector of length m available I is equal to k, means k instance of the resource type I is available in the system. Max m cross n, max I comma j is equal to k, means the process pi requesting the at most k resources, maximum number of k resources of resource type j. Means if suppose that I need, I means I am a process. So I am a process P1, just a minute. If I am a process P1 and I need resource type RJ, resource type RJ of three instances, means I need the process J, means suppose that I have given a number to resource J as 3 or 2. So process 1 requires 3 instance of resource type J. That means 2. Resource type 2, it requires the 3 number of instances. If 2 is given to the printer resource, so process 1 requires 3 instance of the printer allocation. It is again a matrix of n cross m. Allocation means how much resources are allocated to a particular process at any instance of time. For example, of process Pi having k instance of resource Rj. So it will be denoted by this one. Need. Need is again n cross m matrix. It, it is basically maximum minus allocated. Suppose that I have maximum need of the four resources, four instance of printer, and two are already allocated to me. So I need only the two resource of the printer. So this can be find out with the help of the two data structure that are max and allocation. That means that are already allocated to me. Now Banker's algorithm. How will it works? Let the request be request be the request vector for the process pi. If request pj is equal to k, means process pi is requesting the resource j of k instances. Then pi want k instances of the resource type rj. Firstly, I will check if request is less than equal to need or not. Means if I am requesting the four resources and I have need only the two resources, then why I am taking two extra resources unnecessary? So firstly, it will check whether the request is less than equal to or need or not. Otherwise, raise an error condition since the process has exceeded the maximum claim. Whatever the maximum claim I need, I can uh, the resources more than my need cannot be allocated to me. Now, suppose that I request four resources and available resources are only two. So, in that case, the request cannot be granted because system has at present only the two resources and I am requesting four. So, how the system can allocate to me? So, this is not feasible. If my request is lesser than the available, suppose that I request 10 and the system has the four resource, then this will be granted to me. Now, if yes, then the process which have requested the resource in after that, what will happen? Available. From where the resource will be allocated to me. Whatever the system resource have, it will be subtracted from that, means it will be allocated from that only. So now the available will be available minus request. Suppose that the system has four resource and I requested two resource. Now available resource will be 4 minus 2 is equal to 2. So here available will be updated by two resource. Now allocation. Now I have already six resource and two resource are allocated to me from the system. So the allocation will be 6 plus 2 is equal to 8. So allocation will be updated by allocation plus requested. Now, what will be my need? Automatically, my need was initially 2. So need is equal to 2 minus and 2 I have requested and 2 are allocated to me. So my need will be 0. So by this we can calculate the data structure available, allocation and need. If safe state, then resource will be allocated to the process PI. If unsafe state, the PI must wait and old resources, old resource state will be restored. Means resource will not be allocated to me. Now, once the resource allocation process has been checked, now I will check whether the system is in the safe state or not. So for that, for checking that, so initially work is equal work and finish vector of length m and n are taken. Work is equal to available. So whatever the resources are available in the system, suppose that 2, 3 and 4, this is the resource type of A, B, C are available in the system. So it will be allocated to work. Now the work has A, B, C, 2, 3 and 4 and this was the available. Initially, there are five processes or four processes P1, P2, P3 and P4. There are four processes I have taken into consideration. Initially, I will set all as a false because I have not completed the request of any of those processes. So I have initialized with false for all processes PI. I has the value here 1 to 4. I is less than equal to 4. So here I have taken I between the 1 to 4 because I have the process four processes. I will search, is there any process whose status is false? I will search for that. Yes, suppose that P1 process has the status false. I will check whether the required need is less than work, means less than available. If yes, then what will I do? I will go and do. In that case, work is equal to work plus allocation. That means work is equal to work plus allocation. So what is work? Work is the 2, 3, 4, and allocation means suppose that I already have allocation of 1, 1, 1, A, B, C. There are three resource type and I have three instances of each resource. So these will be added. Now the answer will be 3, 4, and 5. Now, resource freed from the process completely. Now, after this, does if the resource that I have holded, that after completion I will release those resources. So the available resource in the system will be 3, 4, and 5. And now, once I have completed my execution, so I will finish. I will set my status as true and go for another loop. Again, check, find out is there any process whose status is false. If yes, then again I will allocate the resource. System will allocate the resource to that process, and after completion of the resources, that completion of the process, that process will release the resources that is it has, and that means it will return back to the system, and that is and set its status to as true. So by this I can find the safe sequence, whether P1, then P2, then maybe possible P4, and then after P3. If there exists a safe sequence and safe, so we can say the deadlock will not never occur if we will allocate the resources in this order. Suppose that after allocating the resource, trying the resource allocation of the resource, P3 will never satisfy its request. So we will say the system will be in the deadlock condition. Whatever the resource I will allocate it in that I have a system, it will not satisfy the request of the P3. That's why P3, that's why the system will be in the deadlock state. So this was all about the safety algorithm. Now I have covered up in this lecture strategies, deadlock prevention, deadlock avoidance. In the deadlock avoidance, how how to deal with the deadlock avoidance with the help of the Banker's algorithm, and then after safety algorithm. So this was from my side. Thank you.